I'm Russell Laux, and I'm a developer on the desktop architecture team. And
I'm Jeremy Wright. I'm the lead product engineer on the graphic system or the visualization system inside of ArcGIS Pro.
And today we're going to be talking about performance and responsiveness. Okay, so we'll start by providing a more specific definition for performance and responsiveness, followed by a brief overview of the core application structure and architecture. We'll then walk through some various diagnostic features that we found useful in troubleshooting issues, and provide some general coding guidance for avoiding problems. And we'll end with listing how you can report issues you haven't been able to resolve on your own. This session is geared towards a developer audience, but it should be useful to anyone interested in peeking in on what's going on beneath the surface while executing operations within ArcGIS Pro. So I'm going to, since the session is concerned with performance and responsiveness, I'm going to take a second to clarify more precisely what I mean by those terms. So performance is pretty much what you would expect it to be, how quickly operations execute. It's objective, it can be measured against benchmarks, and you can do comparative analysis. For instance, you might want to compare how fast some operation is in ArcGIS Pro versus ArcMap. One of the complications for doing that kind of comparison is they are different applications, and sometimes there are different choices made by the developers. For instance, both of those applications support two different label placement engines. One of them being Maplex, a very sophisticated label placement engine, and a faster but simpler basic label placer. In the case of ArcMap, the default is the basic one. In the case of ArcGIS Pro, Maplex is the default. So those are going to obviously have different performance characteristics. So you want to make sure that if you're comparing those two or any feature, that you have them as similar as possible, configured as similar as possible in both of the applications. Responsiveness is a little more subjective. We define it as how quickly the application responds to user commands and how well execution status is communicated. We further classify responsiveness problems.
Next slide.
Oops, gotta keep that going. Okay, we further classify responsiveness problems as GUI hangs, where the graphical user interface thread is hung. You know that's happening because it won't paint correctly. It's frozen, appears frozen. Sometimes you'll get a message at the top on the caption saying that it isn't responding. The other category is what we call a feedback hang, and feedback hangs are a little different, a little subtle. Oftentimes it appears that everything's mostly responsive, but the ribbon or commands will be disabled, and it's not exactly clear to the user what's actually going on, and those can be equally problematic. So that's those terms described. Let's talk about the application. So ArcGIS Pro is a really large application, and I have to talk about a couple of aspects of it, go over some basics of the architecture to make it easier to understand what we're eventually going to get to in the demo. So they took the four previous applications, like ArcMap, ArcGlobe, ArcScene, and what am I missing?
ArcGlobe.
I got them. ArcGlobe, ArcScene, ArcCatalog. That's it.
There you go.
ArcCatalog. So we took all of those applications and combined them into one. I think there's even a couple of extras. And then many of the extensions that used to be shipped separately are now incorporated in the core product. There are over 900 DLLs in the installation of ArcGIS Pro. That's really incredible. There's over 120 executables. And it consists of over 16 million lines of source code the last time I checked. And that excludes the test, any code that's associated with tests, and our third-party dependencies. We naturally don't include those as well. We run over, speaking of tests, we run over 25,000 of them every day. Approximately 3,000 of these are performance-specific tests, and we're always adding to this. Despite that, some performance issues slip by us, and so that's something we recognize and something we're continually working on. Okay, so what is the advantage of having this Swiss Army knife of applications? So you have all the GIS functionality accessible within a single app. That means you can combine discrete functional GIS functional areas, can be combined in novel ways. You also have a shared memory space, so there's some advantages there as far as communication, sharing data. It's simpler to synchronize state, and you know, it's just generally simpler. You don't have things like issues with file locking, as many issues with file locking and those kinds of things. So it's generally has some advantages in that respect, but there are disadvantages. So with something that large, with so many different blades, if you will, modularity becomes an essential characteristic of the application. We can't load everything at startup like a monolithic application would, because we would have very little left over in way of resources to do any actual work. It's also quite complex to have a large number of different subsystems running in the same application. You have to make sure that they don't fight with one another or step on each other's toes and that sort of thing. So there are a couple of big items or characteristics of Pro that often get mentioned in the context of performance, and that is 64 bits and multi-threading. So let's talk about the advantages and disadvantages of each of those. With 64 bits, you obviously get the opportunity to have a very large address space. The previous version of 32-bit Windows was limited to 2 gigabytes, 3 gigabytes, and some later versions, and that's not a whole lot of memory, especially nowadays. If you have a lot of memory, you can take certain kinds of operations and optimize them such that they're not going out to slow disks very much, like loading all the data in at once and doing calculations on that data is a lot faster than going back and forth to disk. 64-bit processes use a different calling convention where registers instead of the stack are used, and registers are very fast. There are more registers in general in a 64-bit processor for faster operations, again, not having to push things into memory as much. And they generally have faster 64-bit and 128-bit arithmetic. Now, the disadvantages. So a 64-bit process is going to use proportionally a lot more memory, mainly because all of the objects that are in memory have an address, and that address is now 64 bits, or twice the length of the original 32-bit addresses. In object-oriented programs like our applications, there are a lot of pointers, and pointers to objects, often those objects themselves have pointers as members that point to other objects and so on. So this can consume a lot of memory. The rule of thumb in general is that you can expect a 64-bit process to take about twice as much memory because of that reason. Another sort of downside is that if you have an operation that really doesn't logically leverage a larger address space, in other words, it has to be performed serially, or it doesn't have a lot of I/O or whatever, it's not going to really benefit from 64 bits. So it's not a solution or a magic solution to improve performance, but it's very good at improving performance for specific cases. Okay, how about multi-threading? Well, you can obviously leverage modern hardware, multiple cores to speed up operations that can be parallelized. And certain operations can be offloaded to background threads that improves responsiveness. The operating system itself, of course, with multiple cores is going to be more responsive. Each application is going to share the machine and resources better. But it has some disadvantages. Multi-threaded applications tend to be much more complex. There's a lot of coordination between threads that has to happen. Of course, there's a risk of deadlocks, conflicts, and other kinds of hazards that are unique to threaded applications. And of course, threads themselves consume resources. Each one has a stack, and there's other overhead that's associated with each thread. And similar to one of the downsides with large address spaces is that not all operations can be parallelized. So not all operations can actually take advantage of multi-threading. I also want to mention one other consequence, and that is sort of the unintended kind. Oftentimes, a developer will try to produce something faster by using a background thread, and they'll want to offload some operation. For instance, we'll just take a hypothetical example, and they have something they want to do on a background thread, some kind of computation, and they have to take the state of the application, and they want to operate on that state. If they allow the user to continue using the system and manipulating that state, that means they really have to take a snapshot of that state. And if the cost of taking the snapshot is very high, so you have to take the snapshot and then run the background thread on the operation to do the computation. If actually making the copy is more expensive than the operation, then you've actually degraded performance instead of improved performance. So you have to be, as developers, we all have to be very careful about the kinds of choices we make when choosing to make something multi-threaded. Okay, now a diagram. So this is a very high-level diagram. Each of the boxes on the screen represent sort of a large functional area like the graphical user interface, geoprocessing, graphics subsystem, and so forth. And the arrows represent threads that are used to communicate between these areas. One of these boxes is rendered in orange here, and that represents this core aspect of application state called the cartographic information model. And the SIM is basically the definition of the project, its maps, layers, how they're symbolized. And these objects also have connections to heavyweight live objects like database connections. And so that represents this really central state within the application. And ArcGIS Pro, like other GIS applications, tend to be very stateful. You perform various actions, and these actions have to be done in the right sequence. I can't, for instance, delete features while I'm still loading the project that will ultimately show me the features that I'm going to delete. So these things have sort of an ordering. So the state has to be maintained in a coherent state at all times. And if there are multiple threads vying for the information that's in the state, they have to be regulated in some way. This is actually accomplished in ArcGIS Pro through a special multiple reader single writer lock called the SIM multiple reader single writer lock. And this is a peculiar kind of lock in that it allows, as in the traditional meaning of that lock, it allows multiple reads and allows one thread to make a write atomically, and it ensures that that state is maintained and correct. But it's a peculiar kind of lock in this case because these, for reasons that have to do with thread affinity and some legacy ArcObjects issues, a lot of these, we only allow very specific threads to participate in accessing this state. So you'll see when we get to the ArcMon demo, you'll see those specific threads. Okay, ArcMon. So ArcMon is a utility, an integrated utility for monitoring and logging various operations as they execute within the application. So there's a bunch of different pieces. I've listed them here, and we're going to go through those. And so that is going to bring us to the ArcMon demo. So let me switch over here to ArcGIS Pro. Okay, here we are, ArcGIS Pro. The first thing to know is how to bring up ArcMon, and the way you do that is through a keyboard shortcut, and it's Control-Alt-M. And it will appear. ArcGIS Pro has to have focus when you press that key sequence. So just something to remember. If it doesn't appear, make sure that you have the application has focus. So the first thing you see up here, notably, is a graph. That graph is tied to this list of counters below here. So each counter, as I go to them, the graph will represent the current value that's in that counter. And these counters, we're constantly expanding these counters, and there are various states within the application that are important for diagnosing performance and responsiveness. Like, for instance, this first one is the task rate, that basically when you're executing tasks like queued task run, if you're familiar with that, those operations go into a queue, and the tasks get executed within the cartographic information model. And if those tasks are coming in at very high frequencies, that's generally a bad sign. So we want to pay attention to the rate. Memory consumption is another obviously important thing. Right now we're using 1.7 gigabytes of memory. That's pretty considerable. But all of these numbers are important, and you can use this graph and the selected item and the graph to kind of monitor their status. This section here is the task log. So as you perform particular operations, like if I say bookmarks, notice that it went to the background. That's irritating. So I'm going to go right click up here and say always on top. That way that won't happen again. And then if we perform an action like bookmarks, like new bookmark, and oops, move this out of the way, you'll see that there's an operation here. It's a little bit difficult to read, but you can see it says ArcGIS Desktop Mapping Bookmark Manager, create bookmark from viewer. Boy, it's a long method. In any case, that is the name of a function that's actually being called in ArcGIS Pro, and it's associated with that task. This is what I generally like to see. A single user action causes a single task to operate. So as tasks are executed, they're logged here, and we keep track of how long, well, first of all, each one has a task sequence ID. This is just an incrementing ID, just constantly goes up. We know that we're at the 239th task since I started. This particular task was queued at this particular wall clock time, and the total task time was 120 milliseconds. So these are all in milliseconds. If you forget, there's a tooltip above each of these that tells you what they mean. The task time is actually subdivided into these three different sections. The task time, this column here represents the time that the task itself, the code that's associated with the task took to execute. The resume time has to do with the graphics subsystem. There's a phase. In some cases, if graphics drawing was suspended, it can later be resumed. And during that time, it's usually very small or nothing, where the task is held up by the resume itself. And then this wait time right here, this one is, notice that the class is called queued task run. That means that it's queued, and when you're issuing tasks to execute against the SIM, they get pushed into a queue first. And so there might be a task already in the SIM that's actually executing, in which case your task that you issue is going to have to wait. If it waits for a long time, that could be significant, and you'd want to know about that. So that's what the wait time is for. And then the function name. This is based on the stack of execution, and that's a little tricky because there's many frames in any stack. A stack is a list of all the functions that were called that were associated with the task. So which one do we choose? So there's a simple heuristic that goes through and analyzes the stack and tries its best to figure out which frame it should pick to represent that task. Sometimes it's wrong. Most of the time it's right. And it will help you identify what actually was happening. The GUI Hang log is an important area, and we basically log every time there's a GUI Hang. We log it, and we log its start time and its duration. We don't log any tasks because sometimes GUI Hangs aren't actually associated with tasks at all, and they're a little tricky to find their cause. The normal way you do it is to attach a debugger, and when you see a hang, you just stop in the debugger. You look at logical thread 0 and see what it's doing, and that's the reason it's hung. Hangs could either be caused by code executing on the GUI thread, which is something we never really want to do. GUI thread's not for executing work. Or it could be that it's waiting on some kind of concurrency lock, and that's also bad. So you can, again, determine that by using a debugger. And finally, we have these status indicators. And each of these status indicators basically indicate some kind of state. And when they're lit up, that's what's happening. And many of them can be lit up at the same time. The first one represents a GUI hang. The second one is a feedback. Remember, we talked about the two different types of these hangs, where the GUI thread actually is responsive, but there's no feedback. So that's what that one is. The task rate, I talked about that in the counter part, but the task rate light will come on to bring your attention to there's a lot of tasks executing. HTTP light just means an HTTP call is in process or in progress. And then if a task is busy, the task busy light will be on. These two here, the view and doc busy, are associated with the graphics subsystem. They define states that are associated with initializing graphics views and uninitializing them or destroying them. And those can sometimes be expensive. And when they're actually happening, these lights will be lit accordingly. The waiting light will be lit if your task is waiting behind more tasks behind it. At least one task is in front of it executing. And then the resuming light is lit when a resumption following previous suspension of drawing is active. So this light here, the GP light, is lit up whenever there is a geoprocessing operation executing. Geoprocessing operations can happen in the foreground or in the background. To tell the difference, you look at this indicator right next to it, and that's the geoprocessing background thread. If that's lit, it means it's a background GP job. So in other words, both will be lit. If it's not lit, then it's a foreground geoprocessing job. These four are very important. These are the SIM threads that I talked about that are associated with that multiple reader, single writer lock. And then the rest of these are all associated with a shared background thread pool. So these are used for a variety of purposes. For instance, if I go in here and I choose, if you direct your attention to this area here, and I'm going to choose like the base maps, and you see they all get lit up, a bunch of parallel operations to go out on the web and fetch these imagery that's associated with these thumbnails, and to generate the thumbnail imagery, and all that was happening on this other thread in parallel. So that's a easily visible case. Okay, so I'm going to switch over to this little add-in, which we're going to include this add-in. This demonstrates some of the common coding mistakes that developers make and how they appear in ArcMon. So that sort of correspondence between what you see and in ArcMon and the actual error that's being made in the code. Before I start activating these, I'm going to show you some code here that is associated with little work functions. These are just stand-ins for various operations. I didn't want to get specific to various GIS operations, so I picked these. These are using spin weights, and the reason I'm using that is I don't want to give up the quantum by doing a sleep, so the operating system is assigning some time, and I want to act like I'm computation, so that's why I'm using a spin weight. Otherwise, for short operations, you're going to end up, you're going to end up measuring the time that you lost by giving up your slice. Okay. So the first case here, the first case we have here is a GUI Hang. So as you might expect, you should probably see this hung light lit. So I'm going to go ahead and activate the button. Notice these are in pairs, just B1, G1. The B means bad, the G means good. So this is like how not to do it, and this is the correct equivalent. So I'm going to click the bad case, and we notice that the hung light comes on, feedback, because there's no feedback either, and a task busy light came on. We also see that it logged the method. So it ran for a while, and it hung. And the reason for that, we'll see when we go over to the code here. So here's the bad one. And what we're doing is in the OnClick method, which is called on the GUI thread, we're actually just doing some long work. This is referring to that spin weight that we were executing within the sim thread pool. But we're doing one of the really, one of those things you never want to do on the GUI thread, and that's call wait on a task. If you call wait, you're blocking the GUI thread. So remember that these are asynchronous tasks for a reason. You're not supposed to wait on the GUI thread. Likewise, if you call result to get the result of the task, that's also going to block. So in this case, that's why the GUI thread hung. The correct way to do this is one, create a progressor so that you can actually see some feedback, and then do an await on the same function so that it's a asynchronous wait. It's not actually going to block the GUI thread. And when it's done, it'll show the same message box. So when we run this one, I'm going to move this over here and execute the good version. We see a dialog. We see a task is busy. We see this guy is executing. By the way, you'll notice it was -1. That means that we don't know how long it's going to take to execute it because it's still executing. So the -1 is there to indicate that it's still running. Okay. So let's go to the next case. This is where you're not providing proper progress, but it doesn't produce a GUI thread hang. So again, we're going to click B2, and you see feedback light is lit, but not the hang light, and a task is busy, and we see the task is executed. If we go and do the good version, we see that there's proper progress appears, the feedback light is not lit, and the task executes. So looking at the code associated with that, we see this. In the OnClick, I do an await, and I pass progressor none. That's not a good idea because however long it's going to execute, there's not going to be any progress shown. So you should always use a progressor. Note that progressors don't have to be progress dialogs. They can be custom progressors that cause some kind of animation, some little spinny. These are anything that lets the user know that something's happening. But no progress is not an option. That's a frustrating experience for anyone. And when this is done, it shows done in the correct version. We actually create a progressor and pass the progressor in to do long work so that you see that progress dialog. Okay. All right, next one. This one I've called hops, and what it refers to is when you make a lot of cross-thread calls. I call these hops. So let's see what happens when I click on B3. We see a progress dialog, that's good, but we see this task rate is really high. And look at all the tasks. There's like thousands of tasks have executed, tons and tons. See, do work, do work, do work, do work. It's like just bad, right? If you ever want to, by the way, if you ever want to grab this list, you can just right click on it and say copy. You can also clear it if you want to start from a known position and get rid of whatever's already in there. Okay, so why did that happen? If we go to the associated code, we see the first version, the bad version, creates a progressor, calls show on it, and then it walks through in a loop and it calls await on the work function repeatedly inside the loop. So in this case, it's going to jump across the thread 6,000 times. So that's not great. This version here makes a little bit of a difference. It goes 6,000 times, and notice it calls all of that, the entire loop inside qtest run, and that's really what we want you to do. If you're going to call some asynchronous functions and you're just jumping from the GUI thread, like in an OnClick or a user interface event, you should immediately say qtest run and do all your work inside that loop. This is going to make one single jump and be done. So how much difference does this really make? So if we do this one more time, up in this right-hand corner, a little message is going to appear. And it tells me that it took 3,611 or 3.6 seconds roughly. If I do the same thing and I don't jump, this guy, and that took 2.5 seconds. So that's pretty significant, and it really adds up. Like, so if you as this number goes up, that overhead's going to get higher and higher and higher. So again, that's why we have that indicator, this task rate, why task rate is the #1 item in this list right here. At the top, it's the default selected one because it's just a bad thing to be happening. Okay, last one. Okay, let's see what happens if I go and execute this B4 command, which says binding. So, all right, the first thing you see is we're in a GUI Hang. Task is busy executing something, and then this doc pane appears with a bunch of results in it. So that something bad happened. If I close this again and I go to the good version of it and I execute this list immediately appears. I don't have any hang. Everything's good. So what's the difference? Well, let's take a look. Okay, the first thing is we have a doc pane in this case, and it has for the list items, it has a list box. That's this guy, and this is bound to the items observable collection. And inside here, like you're supposed to do, you use bind operations to enable WPF thread safe binding through this enable collection synchronization. What this does is it tells WPF, hey, I have this collection and I have this lock, and I want you to know about it. And I want you to know about it because what I'm going to do is on a worker thread, I'm going to add and maybe remove items into this items list. I'm going to add a bunch of stuff on the worker thread. That's good for me because I don't have to jump threads every time I'm adding a string into this list. I can just do it right from the worker thread. But to coordinate that activity, because WPF is drawing that collection, it needs to know about this lock. So I'm on the hook for entering the lock whenever I'm adding or removing or accessing the items that are in the collection. And WPF is likewise on the hook for entering that lock whenever it's reading the collections to actually display them in the list. Okay, so, well, there's potential for problems there, right? What happens if here's the bad case. I went off and ran this function compute, and I jump onto the worker thread and I immediately enter the lock, and then I set in a loop for 10,000 items and I do a bunch of work adding an item to the list as I do each item. So guess what? I'm going to spend a long time inside that lock. What happens if WPF needs to enter that lock to draw something? What's going to happen is it's going to lock on the GUI thread, which is a hang on the GUI thread, which is one of those things we never want to have happen. So entering a lock for a long time actually is a bad thing in no matter what context we're talking about. Even outside of this context, locks should be entered and some resource change, then immediately exited as fast as possible. The longer you're in a lock, the more you're turning some operation that you wanted to be parallel and you're turning it into like a low efficiency serial version of it. So here's there's many options, there's many ways to solve this problem, but here's one of them. In the good case, I go onto the worker thread, I create a temporary little list that I call a chunk. Then I walk through the items, and what I do is instead of adding them to the list, I actually add them to this chunk. So I'm adding them along the way, doing the work, not inside the lock, and adding to the chunk. When the chunk reaches some size, and in this case I chose 100, I transfer the temporary collection into the main collection. I do that in a lock. So I'm in there for a very short amount of time. Notice I'm not doing any work inside the lock. All I'm doing is doing a really quick transfer of 100 items into the list. And that's one way to solve it. You're just trying to chunk up the operations and reduce how much time you're ever spending inside of a lock. Okay, going back to the slides. I kind of want to summarize some common mistakes.
Slideshow button. The slideshow button.
Oh, yep, there we go. There we go. Okay, so the first few that we've talked about already: don't perform work on the GUI thread. Don't call task result or task wait on the GUI thread. That's going to hang it. Use progressors to provide feedback during operations. Otherwise, you'll have one of these feedback hangs where the user won't be clear on what's going on with the system. Reduce hops from the GUI thread by leveraging inlining. So those tasks that are called within a task that's already running, they just simply get inlined. It's no different than calling a function. Use WPF thread safe binding properly and minimize the time that you spend inside of locks. A few that I didn't mention is it's really good to have cancelable operations. If you have, particularly with really long operations, it's a real bummer to set in front of something that you realize that you made a mistake and it's running for a long time, but there's no way to get out of it without like killing the process. That's not what we want to do. So operations that are long running should be cancelable. There are some complications to cancellation. Sometimes, depending on when you cancel the operation, it may have completed several phases that can't be undone. But there's usually an acceptable compromise for almost any operation I can think of where cancellation should be supported. Collection change. A lot of people like collection change notifications. They're essentially events that are tied to collections, like observable collections, and they fire whenever you're adding or removing something. Seems like a great thing to have, but the problem is oftentimes you're in a lock when you're adding or changing a collection because you're using WPF thread safe binding. And if you're in a lock and the event, essentially event code, then does some long operation, it's doing that long operation in a lock, which again, you should never do long operations in a lock. One way to avoid this is never expose collections publicly, particularly observable collections. We, in our own view models, we make sure that we keep those private and we never expose observable collections directly. And that's what I suggest to add-in developers as well. Avoid dispatch or invoke. So this is used when you're on a worker thread and you want to dispatch some operation up to the GUI thread. It's a blocking call. It's a bad operation to perform. You can end up in a deadlock situation quite easily. It's better to plan out what you're going to do and collect information from the user on the user interface thread first, so that you don't have to ask such questions during the operation. And then one real quick mention of freezable objects. There's a category of WPF objects, particularly images, that can be frozen. Normally images, if you create them on a thread, you can only use them on that thread. And I'm talking about managed or WPF-based images. That's pretty terrible. But if you freeze them, then you can share them with other threads. Some people get around this by actually creating the image and then dispatching them. So it's sort of associated with this point where they jump up to the GUI thread to actually use them. That's really inefficient. So it's much better create the image on the worker thread and utilize some of that decoding time on the background, and then freeze them, and then you can use them anywhere you want to. And that's about all I have, and I think I'm going to hand this off to Jeremy, and he's going to talk about graphics.
Thanks, Russell. All right. So, graphics. So, there's a subsystem inside of ArcGIS Pro that the UI interacts with quite regularly, and that's the graphics system, which is what actually draws the maps and scenes and layouts that you see on your screen. So I'm going to talk a little bit about how it works, and then some strategies that you can use to troubleshoot any problems that you might have. Now, add-in developers will typically introduce these kinds of problems, or may run into these kinds of problems when they're developing an add-in that adds things to the map or makes changes to the map. So these are good troubleshooting overall, but also good for add-in developers that are doing those sorts of operations. So how does the graphic system work? Well, Russell kind of went over it with his block diagram there, but the key thing to remember is that it's the display and output system is going to use those data access components to ask for stuff, and then it's going to respond to changes that the application does, changes to the map or changes to symbology, that kind of stuff, by listening to some things that occur. So there's a viewer component which loads the sim storage model for a map or a layout or a scene, and it describes all of the data and symbology in the map, scene, or layout, just like Russell said. When we get those definitions and we load them into a view, we can request the data that we need, the geometry, the symbology, to draw that data in the style that you've chosen on the screen. And when you interact with the map, when you make changes to the camera position, for example, by navigating, those things come down to us, and we say, oh, we need to request more data, we get that data. When those things happen on the UI, like when you change a symbol or when you change the visibility of a layer, we actually get a notification from the application that that's occurred. And you can actually see that in debug. If you have a full debugger attached, or if you just use something like DBG view or debug view, I don't know how to pronounce it, from Microsoft, that'll actually show you all the debug output that's happening in the system, and you can kind of get a visibility into what's going on. That's a good way to troubleshoot, actually. If some change to the view isn't occurring in the code that you run, and you're not seeing it happen, you can check and see if the notification is getting passed. So there's, just like in the UI or in add-ins, there's also two types of issues that can occur. There's responsiveness, and in graphics terms, that usually means when things feel sticky. The frame rate has gone down, and because of that, when I try and navigate, it doesn't feel like it's listening to my inputs. The other category of these kinds of problems is performance, of course. It takes a really long time to draw this map or this scene or this layout. And then there's a loading indicator. So remember, Russell mentioned progressors. Our progressor is the little swirly thing at the bottom right of your map view and layout view that swirls to tell you that things are still occurring. We're still loading data, we're still drawing it, etc. It's right next to the pause drawing button on the lower right of any view. So most of the time when we look at these things, performance issues are going to be related to some latency in either data access or the data source itself. So some of the tools that Russell already showed with ArcMon can help to diagnose these. You can watch for the HTTP indicator to see if your WebGIS data is taking a really long time to come over the wire. If you're really interested, you can actually use Fiddler to monitor the status of those requests. If a lot of them are coming back as 404s or 504s, or there's errors that are occurring, then that could tell you that there's some problem with the server or portal that you're accessing. For the enterprise geodatabase, you can actually have your DBA or anyone who knows how to actually do trace diagnostics on the database itself to detect when there's issues with data access. And then for local data, the best strategy is going to be use something like Task Manager to see if disk access is constraining your drawing of a view. It's not that common, but it can occur. Responsiveness problems, we've actually put a lot of safeguards into Pro to try and warn you when those things are occurring. Try and kind of like a fail-safe, so if you try and do something that's going to result in a lot of drawing or a lot of problems with drawing, then we're going to warn you. And those will show up as a toast notification, as they're called, in the upper right of your Pro window. It's going to say something like excessive drawing requests or GPU resources exceeded. These are all actually links in the slides that you're going to have. These are going to be links to the help topic, so you can read more about those problems. You can click on the error when it occurs. But what they all boil down to is probably trying to do too much. Either there's too many triangles on the screen, or you're trying to do too much for your integrated GPU, et cetera, et cetera. There's also some hard errors that occur, like when the graphics driver actually errors out. When that happens, you get changes in graphics hardware detected. That can happen intentionally, for instance, if you undock your machine from an external GPU, or it could happen unintentionally when something happens that causes your graphics driver to crash. In those cases, of course, we want to check and see if the driver's up to date, all those sort of normal GPU troubleshooting things. But it could actually be that the code is causing something to occur that's going to cause an error. And then lastly, no compatible graphics adapter detected. Probably if you're running this on a normal machine, you're going to have a graphics adapter of some sort that has some acceleration capabilities. But if you run ArcGIS Pro on a machine that has absolutely no GPU, or a GPU that doesn't support the levels of DirectX and OpenGL that are required, it's going to fall back to something called Warp, which is a software emulated rendering that emulates a GPU using your CPU. It'll still draw, but it's going to take a lot longer because, of course, a CPU is not as efficient at operations that a GPU is going to be efficient at. So, there's other tools that you can use to help with graphics-related issues. So first off, whenever you're actually trying to look at a graphics problem, or actually even a problem in Performance in Pro, you should always check to make sure that the machine you're running on actually meets the system requirements. These are updated every release, so we try to keep them up to date. And there's also an automatic tool that you can run that'll give you a snapshot of your hardware config, including areas that may need improvement. Obviously, if you want good performance, you're going to want to shoot for the recommended spec. This is a basis, not like a guarantee. Even if it meets recommended specs, it may be a particular kind of graphics card that actually has a lower performance, for example. Things that are meant to run multiple monitors, it's not necessarily 3D acceleration. They'll still support those APIs, but they're not necessarily going to give you the performance that you want. And so to measure that, we have some tools. So Shift-E, we don't have anything other to call it than Shift-E because we already took ArcMon. But Shift-E actually brings up a readout that gives you a lot of stats in the current view that are related to drawing. What kind of API we're using to interface with the graphics card, DirectX or OpenGL, how many triangles are on screen, the average frames per second, the instantaneous frames per second as sampled at an interval, and other kinds of things like memory transfer rates. All those things can be useful diagnostics either for you or actually to send into tech support if you find a performance issue. And then, there's a tool built into Windows, actually. Task Manager has a performance tab. That'll actually let you monitor resource availability and usage for many parts of your system, CPU, RAM usage, disk usage, and usage of a specific GPU as well. It's really useful for troubleshooting display problems or problems in general. So there's a larger blog here that goes over some more of these strategies overall, both things that Russell described and the things that I'm describing. So there's a link here to go to that blog. It was last updated in 2016. We definitely owe you an update, so we'll get on that. We'll get on that as soon as we're done recording this video. All right. So now is the time for me to do a demo. So, wow, there's a scaling issue there. Huh? All right, so here's a Pro 3D view. This is San Diego with a Dornier flying boat in the water here. It's a pretty complicated view. I've got a lot of stuff going on here. So there's some things I wanted to show you. So first off, if I hit Shift-E with the map view focused, so just like ArcMon, I have to have the actual view focused, it's going to bring up these statistics at the top of my screen. Like I said, that's going to tell me that I'm rendering using DirectX 11, what my rendering quality slider is set to, my instantaneous frame rate, my average frame rate, and then the number of triangles number of triangles that are displayed per frame. As you can see, I've got about 20 million triangles on the screen, so this is a super complicated view and a lot of stuff going on. The other thing you can notice, it's actually going to tell you memory usage here, and texture memory usage here, and then transfer rates, as well as the number of tiles that are being used to display the actual surface. This is elevation under E and C. It'll even tell me the resolution of the view that I've got displayed right now. So it's 1362 by 766. So all of these are things that you can use to diagnose problems. So for instance, when I try and pan and zoom, I can see that the numbers change as it samples, and I'm going to get some different numbers. If I wanted to troubleshoot, I could actually turn off a layer, for example, the trees layer, which I know is using a lot of triangles. And once that's done and it starts to update, I can see that the number of triangles goes down and the frame rate goes up a little bit. So other ways that you can kind of take a look at this, if you go to the Task Manager, like I mentioned, it actually has a graph that shows the usage of each of your components, the CPU, memory, and the GPUs that are on the system. Now, this is a machine that has switchable graphics, so I actually have an integrated Intel graphics card, and I have a dedicated discrete GPU chip that's being used. Both of those could be used, and for NVIDIA graphics cards, there's a compiled-in variable that lets it automatically switch to the hardware acceleration or to the dedicated acceleration on automatically. For AMD GPUs, up until the most recent driver update, there isn't an automatic switch, so you actually do have to open the Radeon Switchable Graphics Adapter utility and tell it to use the high-performance GPU when you're running ArcGIS Pro.exe. So if you come in here and you see that all the GPU usage is on the Intel graphics card, that's probably why you're getting pretty bad performance versus your high-performance graphics card. Just another thing to check. And then we also mentioned debug DBG view. I don't even know how to pronounce it.
I always say debug.
Okay, debug view. Let's bring it up. So this is a sysinternals application that's distributed by Microsoft. And what it'll actually do is it's everything that's dumped out to the debug console is actually displayed here, including stuff that's not on Pro. But the thing I wanted to show you was if I make a change to the view, such as turning off the cars layer, I'm going to see some notifications that tell me that something changed and it's being communicated to the graphics system. So remember, Russell talked about how when I make changes to these data structures in the sim, I get a suspend, meaning, hold on, things are going to change, so you need to stop. A notify change that tells me what's happening. So in this case, I know that an update's going to happen to the list of layers, notify change layer update. And then sometimes there'll be a hint that can optimize what changes are being made. So changes to visibility. If I make changes to transparency, we do it in an optimized way. Once those changes are done to the sim, the application says resume, and when that happens, we can start drawing and be done drawing. That's what these two notifications here are. So if you run into a situation where you're getting a lot of these communications, you can actually see that something's maybe going wrong. I think that's everything I wanted to cover. Let me go back to the slides here.
There was that contact. Let's see here. Where should our customers go if they're experiencing performance problems?
Okay, that's a good question. So if you're experiencing performance problems, there's several different ways you can go about this, and that's actually almost any problem actually that you have with ArcGIS Pro. You can contact technical support directly. That's going to provide you with interactive troubleshooting of the problem, and in most cases, that's probably the best way to go. You can also use the user-to-user forums on GeoNet, and what that is it's a forum that anybody that wants to use Esri software can go to, and maybe, hey, I've had this problem and I have this particular thing that I'm doing. Has anybody else had this problem occur? So it's a way of communicating with other users and also Esri staff, but it's not necessarily going to be officially monitored every day by Esri staff. If you run into a performance problem and you wanted to have some troubleshooting done, or if you have questions about this presentation, then going to, let me bring up the slide actually because I'm still displaying my screen. Here we go. We are professional presenters, as you can tell. All right, so if you do run into performance problems, or if you have questions about this presentation, go to GeoNet and make a post that says, hey, I saw this presentation and I have this question, or I'm running this performance problem and here I'd like some ideas. Some people, that when you mention us specifically on GeoNet, we can actually see that, we get notifications, and we can go and answer you directly. If you have a problem that's beyond our expertise, or maybe requires more interactive troubleshooting, we're probably going to tell you to contact Esri technical support. When you do that, please provide as much detail as possible. So like Russell talked about the log from ArcMon if you're having a responsiveness problem in the UI. You can copy and paste that out and send it in. You can send in a screenshot of your can you run it so they know already your configuration and that you meet the system requirements. If you have specific workflows that trigger a performance problem, you can actually include those steps so that we can actually reproduce them in development. And then, of course, if there's actually data or your add-in, for example, that's necessary, providing that sample code so that we can run through those scenarios is obviously invaluable in reproducing those problems. We definitely want to help, and we definitely want to solve any problems that are actually a result of bugs in the software. And of course, we also want to help you solve problems that might be in your own code and your add-ins. So both of those are invaluable, but just keep in mind, go to GeoNet, but also contact with tech support if you need something a little more immediate. Tech support's response times are usually pretty good. So I think that's everything
about
we got.
it.
Yeah.
We wanted to answer questions, but that's a little difficult in this format.
Yeah.
But apologies for that.
Yeah.
And hope you enjoyed the session, and we'll hopefully see you next time in person.
All right.
All right.
That's it.
All right.
Thanks, Russell.